All right. Hi, everyone. Welcome. We are continuing on with our basic fundamental circuit stuff. Last time we looked at series circuits. We learned how to calculate power. We learned Kirchhoff's voltage law, and things like resistance in series adds. So we're going to build upon this, and we're now going to get to the other side of that coin, parallel circuits. So you have series circuits, you have parallel circuits. Now, no matter what circuit you look at, it takes more complicated circuits take in elements of series and elements of parallel, and then they all kind of merge together in one big elaborate design. So we're going to be focusing today on parallel circuits, and then next class we're going to be merging the two series and parallel, and then just building up from there, and then we'll get into all of our cool analysis techniques. So parallel circuits, what are they? First off, a parallel circuit looks like this. Okay, let me go list this as R1. Let me list this as R2 and R3. And of course, we can put as many things in parallel as we want. And the kind of characteristic, sort of, if we're going to ask ourselves the question of, well, is it in parallel? We should be asking ourselves, is one side of a component, in this case R1, is one side directly tied or directly connected to one side of another component, and then is that other side also connected to the other side of that component? Okay, so look at this side, look at this side. If the two are connected together, 100%, they're in parallel, right? Okay, now of course we can get a little more specific than that. So let's go ahead and kind of list these characteristics. There's only two that we really need to remember, and even one of those is the most important one. So first off, there are two or more paths for current to flow. All right, two or more paths. Okay, now if you remember with a series circuit, there was only one way for that current to go, right? So if you're looking at a series circuit, the current going through here absolutely must continue through here. Think about it as a pipe. There's only one way for stuff to go, okay? In this case, the electrons. There's only one way for this current to flow. Now, in a parallel circuit, there are two or more paths for current to flow, okay? So, the current entering here has to make a decision. Some of it will go this way, the rest of it will go this way. Okay, so current splits. Think about that. The current splits, and we will talk about how it splits. But I will tell you right now, if this is IT, and if this is I1, and if this is I2, then we absolutely must say that IT equals I1 plus I2. There's a specific name for this, and we will get to it later, but just in case that thought crossed your head right now, absolutely, if some of the electrons go this way, the rest of the electrons must go this way. And so I1 plus I2 must equal IT, right? Everything must be conserved. Okay, and we will talk more about that. But nevertheless, there are two or more paths for current to flow, as opposed to only having one path in a series. Okay, now this next one is probably the most important one. Well, no. They're both important. Don't get me wrong. But this next one is going to be one of those that's easy to forget, and it's really helpful and useful for solving any circuit where you have parallel elements. The voltage is the same across all parallel branches. The voltage is the same across every branch of a parallel circuit. Okay, again, the voltage is the same across all parallel branches. Okay, branch. First off, I got a branch here. I got a branch here. Okay, branch, just fork in the road. So if I have two things that branch, they're in parallel, then the voltage is the same across all parallel branches. This means VR1, VR2, VR3, they're all equal to each other, okay? VR1 equals VR2, which equals VR3. Okay, now let me go ahead and kind of give a practical example. This is one of those examples that I think sticks out in my head and sort of solidifies this idea. I'm going to call it the car example. Now, anybody know how many volts your car uses? 12, right? Okay, now somebody asked a good question. Is this assuming R1 equals R2 equals R3? Doesn't matter. I don't care what the resistances are. If they're in parallel, they have the same voltage across them. And we'll be going over that over and over again. Okay, so somebody said your car runs off of 12 volts. Absolutely, my car runs off of 12 volts. Okay, now give me some things you have in your car. Radio. Yeah, screw the ignition system. I just want to listen to my music. Okay, I got a radio. How many volts do you think that radio runs off of? Yeah, exactly. 12 volts. My radio is designed to run off of 12 volts. What else do I have in my car? Headlights. Yeah. There's also dome lights, there's rear brake lights, there's your headlights. All right, how many volts do those lights work off of? 12. All right, give me something else. Window wipers, yeah. My window wipers, the motor that actually moves. By the way, as a little side note, if you're ever looking for a cheap motor that has a lot of torque, like you want to move a big project or something, look at windshield wiper motors. You can find them for like 20, 30 bucks used, and they are beefy and have a lot of gear reduction in them. They're great for future projects. Okay, so my window wipers, they work off of 12 volts as well. Let's throw in a couple more things here. We have horns. You gotta honk at those people that cut you off. That's also 12 volts. Let's go ahead and mention, we got an ignition system. We have spark plugs that need to fire in order to make those cylinders move. Somebody is saying the butt warmer. Yeah, the butt warmer. By the way, whenever one of those turns on and I have no idea, I I get the sense that I just wet myself. I've been in a friend's car and it was like the seat warmer was on and I'm like, what's going on? Okay, so absolutely the ignition system. My gauges, my butt warmer, all of that stuff runs off of 12 volts. The way it all gets 12 volts is that they're all in parallel. Okay, so for whatever reason, I just feel like this sticks in my mind. My car is a 12 volt system. Everything runs off of 12 volts. And so they're all in parallel. Okay, so that's just kind of a good example. So reiterating, we got 2 or more paths for current to flow, and the voltage is the same across everything that is in parallel with each other. We good? Okay. My lights on the dashboard are 12 volts. Okay, let's see. So we know they all get the same voltage, but what does differ is how much current each one gets. Let's do an example. Okay, I'm giving myself a 10 volt source and 2 resistors in parallel, an R1 equal to 10 ohms of resistance and an R2 equal to 5 ohms of resistance. Okay, and the way we are applying the polarity, the bigger side of this constant voltage source is always the positive and the smaller side is always the negative. And so, what do we know about this circuit already? It was number 2 of the characteristics. What's the same across them? Yeah. So I jumped straight to the answer. Where did I get this 10 volts from? Because 10 volts was being applied. But they're in parallel, okay? So not just my resistors are in parallel, my voltage source is in parallel with R1 and R2. So my voltage source is also a component. It is in parallel with R1. And therefore, if they're in parallel, they better have the same voltage across. Now, since this guy is the only thing applying the voltage in this case, I have 10 volts. This has 10 volts. This has 10 volts. Okay, so they all have the same voltage. 10 volts was given, but it's in parallel with R1. Therefore, R1 must also have 10 volts across it, and so must VR2. Okay, so that right there, great usage of our second characteristic, or that really important thing that I mentioned. So now we get to what does differ. Current, okay? Current is not the same for every branch in a parallel circuit. Okay, so now we need to go ahead and figure out what the current is. Now, I'm going to go ahead and put some things up. The first one is I'm going to have some current leaving my voltage source. It's the current for the entire circuit. Therefore, I'm going to call it IT for total current. You can call it I, you can call it I1, you can call it anything you want. But for the sake of convenience in this class, I will be calling the current for the entire circuit. I will always be referring to it as the total current. Okay, so that's the current leaving the voltage source. Now, the current has a choice. Think of this as your fork in the road. I can have my current go this way, and I can have my current go this way. In other words, the current will split. Now, I'm going to go ahead and I'm going to label these as IR1 and IR2. I did that because, well, IR1 is going through R1, so why not? That's the current flowing through R1. And IR2 is the current flowing through R2. Now, notice you follow this path over here to get to R2, but the current that's leaving this point right here is the current going through R2, hence I will just call it IR2. Okay? So essentially, I have three currents in this circuit right now. So, can we go ahead and solve for any of these values? Can I solve for IT? At least, not directly just yet. Can I solve for IR1? Absolutely. What law is going to help us with finding IR1? It's Ohm's law. Okay, Ohm's law. Now here's the trick with Ohm's law. Make sure you're only using it for the values involved for one component. Okay, so for Ohm's law, because I know the resistance of R1 and because I know the voltage across R1, I can now find my third property, my current through R1. Okay, so just make sure before you answer the question of IR1, are you dealing with only the resistance and voltage regarding one component? If you can do that, you can use Ohm's law here. Okay, so now we can figure out what IR1 is. Now, V equals IR, Ver. So I can go ahead and say V divided by R gives me current. So let's go ahead and set it up that way. Okay, so IR1 is equal to VR1 divided by tongue twister, R1, right? So I is equal to V over R. It's the same thing as this equation. Let's go ahead, plug in our values, figure out what IR1 is equal to. VR1 is just equal to 10 volts. We figured that out because we know that everything in parallel has the same voltage across it. And R1 is equal to 10 ohms, given by the problem. Therefore, what's my current equal to? 1 amp. Make sure you keep the units straight. Okay, so now I know the current going through R1. All right, next up. Can we figure out what IR2 is equal to? Yeah, of course, it's the same exact thing. Just Ohm's law. We have the resistance of R2. We have the voltage drop across R2. We can find our third property, IR2. Same thing. IR2 is equal to VR2 divided by R2. The voltage drop across it, well, again, it was in parallel with this, so we knew that it was 10 volts. And we know the resistance of R2 as given by the problem to be 5 ohms. Therefore, what is the current going through R2? Well, 10 divided by 5 gives us 2. 2 what? 2 amps. Okay, so that's how we used that property of parallel circuits, being that they have the same voltage drop across them, in order to get to our currents using Ohm's law. Now, what we haven't answered yet is, what is IT equal to? I already alluded to this. If you think about this situation, I have some number of electrons entering this point. Some of those electrons go over here, and the rest of the electrons go over here. Or some of the electrons go over here and the rest of them go over there. It's all the same. What's going to matter is that IT is equal to IR1 plus IR2. Okay? This is an idea of conservation of charge. I cannot lose electrons and I cannot gain electrons in this circuit. Meaning I cannot lose electrons when it splits. There's no electrons flying off of the wires. There's no electrons flying off of this paper. There's no electrons going up. The electrons have to go through this wire. And so current or charge ends up being conserved. IT therefore is equal to IR1 plus IR2. Or in this case, 1 amp plus 2 amps, which equals 3 amps. Now, there is a name for this. Just as Kirchhoff developed a voltage law, the sum of all voltage drops in any closed loop is equal to 0, just like we saw at the end of last lecture. Well, he's got something to say about current as well. Kirchhoff's current law Kirchhoff's current law states that the sum of all currents entering a node must equal the sum of all currents leaving that same node. Okay, I'm going to write that out in a second, but I'll say it again. The sum of all currents entering a node, and by node I mean some junction that has multiple wires connected to it. So the sum of all currents entering a node, which in this case is only IT for total current, must equal the sum of all currents leaving that same node. In this case, I have two currents leaving this node, IR1 and IR2, and the sum of them is just IR1 plus IR2. Okay, I'm going to go ahead, redraw this circuit. I'm going to remove the resistances, the voltages, and I'm just going to look at it from the case of current so we can focus a little more on KCL. I already did what I said I wasn't going to do. It's early on enough. I'm going to scrap this paper. I will use it again for some other trick. Maybe a paper airplane. Okay, now let's go ahead and write in our currents again. Okay, so KCl. States that the sum of all currents entering a node must equal the sum of all currents exiting this same node. Okay, how many nodes do I have in this circuit? Well, I got 2. Just going to call them node A and node B. So let's go ahead and let's talk about node A. Now look at what's happening in node A. IT is entering, IR1 is leaving, and IR2 is leaving. If you notice what's happening, current is splitting, okay? Some of the current's going this way, some of the current's going this way, okay? It's getting divided. So we actually call this a dividing node. Okay, so we end up with this Kirchhoff's current law expression that states 3 amps equals 1 amp plus 2 amps. Okay, so the sum of all currents entering a node must equal the sum of all currents leaving that same node. But the current is being divided. Okay, so you can kind of think of this as a current divider. Okay, now that's node A. We haven't said anything about node B yet. Now notice what's happening in node B. I have IR1 entering and I have IR2 entering. And I haven't written down what's leaving. I'll call it I3 for now, but you'll see that I'll end up calling it IT because it is IT. Okay, now in node B, if we go ahead and zoom in on that one, I have 1 amp entering and 2 amps are entering. And then I had a third current. I just picked an arbitrary number and called it I3. And notice what's happening here. 2 currents entering, 1 current leaves. This is a summing node. We are adding the current together. So in this case, if we want to answer the question of what is I3, we can write a KCL expression. Well, now you can go ahead and really easily see that I3 is equal to 3 amps. And you also notice that 3 amps is the same that was leaving that voltage source. I have 3 amps coming back into that voltage source. This is always true. The current leaving this voltage source should equal the current that's entering back into that voltage source. Now, normally I don't even write I3. I don't bother. I just call it IT again because I know that that's going to be true. So if you know the current leaving a voltage source, you already know the current entering back in that same voltage source. Okay? So we have a summing node and we have a dividing node. Those are just some words that I'll throw around when we're looking at how current is splitting. Okay? So in one case, you have current being divided or a current divider. And in the other case, you have a current summer. Okay? All right. Does this make sense so far? Do I have any questions? Cool. I'm glad it makes sense. At least for one person that said, yes, it makes sense. And now for 3 people, 4 people. Okay, let's see what we're doing next. Resistance in parallel. Okay, just like we saw how resistance in series adds, resistance in parallel will do something too. So just like I drew an equivalent resistance or a total resistance for 2 resistors in series, I can do the same thing. Come up with an equivalent resistance or a total resistance for 2 resistors in parallel. Okay, so I can combine my resistances. Again, I can go ahead and do a reduction and make 1 resistor that's equal to 2 resistors in parallel, or 3 resistors in parallel, or the sky's the limits. However many resistances I have in parallel, I can merge them all together. Now, the general formula to do this is RT is equal to okay, for as many resistors as I have, I can take the inverse of the sum of the inverses of the resistances. Okay, a little awkward to punch this guy into your calculator. There is another formula to get the same thing. It only works for 2 resistances, however. I can do the multiplication over the sum. Okay, so if I have for just 2 resistors, I can multiply them together, R1 times R2, divided by R1 plus R2. I use this equation the most. This is the easiest to punch into your calculator. Okay, so I tend to like this equation. And if you do have 3 resistances, you can merge 2 and then take that one and then do the same calculation again with the third one. So you can use this equation for multiple resistances as well. You just have to apply it multiple times. Now let's go ahead and let's do an example of this. Let's say I have 10 ohms in parallel with 15 ohms. Okay, so can I go ahead and merge these resistances? Of course. So I can go ahead and create one equivalent resistance or a total resistance, which is equal to 10 times 15 divided by 10 plus 15. What does that end up being equal to? 6 ohms. Okay, so for all practical purposes, there is no difference between this circuit and this circuit. Okay, so resistance in parallel, use these two equations. Now let's go ahead and let's use this for a circuit. Let's go ahead and say I have a 75 volt voltage source. I want to make that larger. Let's say R1 is equal to 100 ohms. R2 is equal to 300 ohms. And this is all I got. Here's my question. Okay, can I figure everything about this circuit? Now, when I say everything, or when I say solve the circuit, I'm saying, can I figure out the voltage drop across every component? Can I figure out the current going through every component? And if I have those, can I figure out the power being dissipated by every current? And so in this case, can I do that given everything that I know thus far? Absolutely yes. Okay. Now, first off, I think a good approach to any problem that looks like this, solve for RT first, okay? That would be my first thing that I would do, just looking at this. And you'll see why in a second. So can we reduce the circuit? Sure, I can come up with an equivalent resistance for these two. It's just going to be 100 times 300 divided by 100 plus 300. Now solve that out, you're going to get 75 ohms. Okay, now that we have a reduced circuit, redraw it. So one of the things I'm going to advocate is to get in the habit of drawing your circuit and filling out on that circuit as you solve. I have never found it helpful to create a list of all of my equations and then try to keep that in my head in regards to what the circuit is doing. So what I do is I redraw the circuit and then I backfill my information as I get it. Okay? So I always start with a fresh sheet of paper, redraw that circuit, and then I start solving and I fill in with arrows and values on the actual circuit, and that helps me to train my solution approach. Okay, so we've done this. Let's go ahead, let's redraw it. Okay, can I figure out my total current at this point? Absolutely. Okay, so my current is leaving this voltage source and going through that 75 ohm resistor. Sorry, I didn't make this bigger, so I can't draw it on the inside. Okay, so this is my total current for this circuit. If I know my total current for this circuit, given that this circuit is identical to this top one, we'll just forget I did that. Given that this circuit is identical to this one, if I figure out the total current for this circuit, I know my total current for this circuit. Okay, so let's figure out what IT is equal to. We just use Ohm's law for that. We know the voltage applied and we know the resistance, so we only have 1/3 quantity to solve for. So IT is equal to 1 amp. Okay, if I know the IT for this one, I know the IT for this one because they're the same. All right, now what? Well, I'll tell you what I do know. I just can't find it yet. I know that that total current is entering this dividing node right here. Some of it's going this way, the rest of it's going that way. I'll call this one IR1. And I'll call this one IR2. And if I want to be a little facetious, I can draw it just to emphasize that the current's coming all the way from here. Okay, now, shoot. Well, my current is dividing. Now, what I do know, I can say that the current is being divided by the ratio of these resistances. And we know that resistance and current is inversely proportional, meaning that the lower the resistance is, the more current I have going through it. And you may have seen in another class or another electronics class that you can go ahead and figure that out. You can divide the resistances and multiply that by the current entering, and then you can figure out how much current is going this way. I think that approach is unnecessary and is just another elaborate extension of just what we already know. We already know how to get at the answer here. We got that in the first slide or the first part of this lecture, which is if it's in parallel, it's got the same voltage drop across it. So it's actually the same thing we did before. So I can figure out what VR1 is. Because it's in parallel. Well, R2 is in parallel with R1. They should have the same voltage. Okay, can I go ahead and figure out these currents now? Absolutely. Use Ohm's law. IR1 is going to be equal to 0.75 amps. I just did Ohm's law. Okay, so I did 75 volts divided by 100 gives me 0.75. I'll do the same thing over here. Do I need to do that? Or do I already know how to get this answer of IR2? Thank you. Yeah, exactly. I can go ahead and subtract, okay? So I don't need to use Ohm's law in both of these cases. I just needed to know how much current is going in one direction. Once I know the current going in one direction, I can go ahead and use KCL to answer the question of what IR2 is. By Kirchhoff's current law, we know that 1 amp is going to be equal to 1 amp. The sum of all currents entering a node must equal the sum of all currents leaving that same node. So 1 amp is equal to IR1 plus IR2. So we know that it should be 0.25 amps. Let's put that in here. Now, was that the only way to get this answer? No, I could have also used Ohm's law. Now, here's the cool thing. We are building up a consistent set of rules, just like in mathematics, right? You learn how to add, and then you realize, well, multiplying is just repetitive adding, and subtracting is just, adding a negative value. It's a consistent system. It's an entire set of rules that should all agree with each other. So if what I'm saying here is all accurate and true, then no matter what approach, you should get the same answer. And here's a great example where I have two ways to get that answer. KCL tells us that this is 0.25 amps, but I could have also used Ohm's law to figure that out. So let's go ahead and do that and make sure that this is all consistent. All right, 75 divided by 300. I can't do that in my head, so let's switch to desktop view. Actually, no, I will do this instead. Aha. All right, and I'm going to go ahead and punch in 75 divided by 300, and I sure hope that I get 0.25, because if I don't, we're in big trouble. Sweet. Okay, so we get 0.25, the same answer as if we would have solved for that value using KCL. Okay. Do I have any questions at this point? All good. Perfect. Okay, so let's go ahead and let's end class here. We have covered series circuits, we've covered parallel circuits, we've covered Kirchhoff's voltage law, Kirchhoff's current law. What else? Series resistance adds parallel resistance does that reciprocal inverse equation, or the more simplified for two resistor case of the multiple over the sum. And current is the same at every point in a series circuit, and voltage is the same across every branch of a parallel circuit. Okay, those are everything we've learned thus far, and that actually is everything that we need for most of the semester. I'm going to list these out. Current is the same at every point in a series circuit. I will abbreviate it as I, same for series. Okay, I said voltage is the same across every branch of a parallel circuit. I will abbreviate that as V, same for parallel. Ohm's law. Need I say more? He's the star of this show. We have Kirchhoff's voltage law. We have KCL, Kirchhoff's current law. And we have that power equation that I could always kind of consider as an afterthought. Okay, so thus far, this is everything we've learned, and if we are super comfortable with all of these, we can solve any of the circuits that we're going to see, okay? So let's go ahead, let's stop here. I will pause the recording, and we will take 10 minutes, so we will be back at 10:40, maybe a little more than that, but the lab that we're going to start today is on the website. Go to the website and get the next lab. I need to update the due date for it, and we will start on it today, and I will be around to answer questions. Okay, so get started on that. I'm going to take a 10-minute coffee break here. Okay, so I will see you there. Question, are the problems on the website homework or for practice? Homework is practice. They're the same. Okay. I won't be collecting homework. Homework is one of those things. Do it, get a head start on it. If you start the homework, a day or two before the exam, it's way too late. You need to build up that practice now and get comfortable with these. So although each one of these is super simple by itself, once you start putting them all together, things start getting complicated and out of control real quickly. And the only way to mitigate that elaboration or that exponential growth of complexity is to start with that homework. Okay? We will be getting to breadboards. However, keep in mind, I'm still waiting for information on lab supplies for this class. We're supposed to have some checkout system, and I haven't stated any supplies to buy for class. I get the feeling we may start halfway to 3/4 through the class. We're just going to have to see what happens. There is... you can buy parts, but the problem is you're not going to have a benchtop power supply. You're not going to have oscilloscope, function generator. You're not going to have that lab test equipment, and it is kind of pricey. And in fact, this is one of the reasons why I'm putting together that live streaming session, the $100 electronics workbench, for all of the test gear that you do need. Or not that you do need, but all of that test gear that would be nice to perform any type of electronics experiment and troubleshoot your project down the line. That's aside from the class. That's not a requirement for the class. The requirement for this class are those labs that are posted up on the website and mainly dealing with the simulation. Okay, so let me go ahead, take that 10-minute break. I can answer many more of these questions in lab at 10:45. Yeah, your Arduino kit does have most of the supplies except for the test equipment. So if you are in 262, you're already starting to build up some home test gear. There's no way around it. There's no way avoiding it. You're going to eventually buy some things and put together some type of kit. So, if you're in this major, you probably should be loving this stuff and collecting these little tidbits in order to make these awesome projects is just part of our experience. Okay, so I will see you guys in lab. Thank you so much.